Okay, well, it's a pleasure to be here. And just to reiterate, Jeff, it's really good to see all the old faces, the old friends. It really brings a warm touch. For many of you whom I've met back in the IBM days, have become friends. Even though we may not be working the same team, but I know you guys are there. So, okay, today let me introduce you the work that my team here in Huawei have been working on for the past year and a half, is optimizing SQL programs with MLIR for AI accelerators. So this is the agenda for the talk. I'll give you a little bit of motivation, the background. In this part, I'll describe the Huawei DaVinci architecture. And then I'll quickly move into the Syclops, the Syclops converters that we have developed in-house. Some of the key parts about this converter is that it performs very well program reconstruction to reconstruct the block, control flow reconstructions, the shapes of the buffers, and even the iteration space of the parallel for constructs. And I'll dive a little bit into the MLIR optimizations. After all, we do rely heavily on MLIR to optimize for us, and we spend quite a lot of effort in developing our own dialects to support the accelerator, the DaVinci architecture. And I guess I'll dive a little bit into the affine loop tile and data copy generate, these passes, especially the loop tile phase if time allows, and some of the interesting work that we are working in the affine dialect. Performance, that's one thing I won't cover in this talk. Please refer to our papers. There are comprehensive charts and numbers there for you. Okay, first, SQL. So SQL is, as we know, is a Chronos cross-platform abstraction layer from Chronos that enables host and kernel code to be written in a single file. So it's the future for heterogeneous computing. So we have been looking into SQL. And since SQL has its lineage from OpenCL, it inherits an SPMD-based programming paradigm for the device kernel. While SIMD SPMD has gained tremendous amount of popularity due to GPU programming, SPMD for many cores or even for accelerators remain an active research field. And we have surveyed various techniques, whole function vectorizations and whatnot. We felt that to address SPMD, generate efficient code on a traditional SIMD units, an accelerator that has a traditional SIMD units, and requires explicit memory hierarchy management, that part of the work is pretty empty, and it's the place where we can do our research. Let me explain a little bit what is explicit memory hierarchy management. So that leads us naturally to Huawei's DaVinci architecture. So the DaVinci architecture, as shown in this very simple diagram, has an L1 buffer and unified buffer serving as on-chip lower-level caches. The exchange of data between the L1 buffer and the unified buffer with external memory, the global memory, needs to be efficiently orchestrated by software. So software in this place is the compiler. It's proven to be very difficult for the reason that on CPU, we enjoy memory subsystem. You count on the cache coherency mechanism to manage the cache, the data movement for you. But in this architecture, we don't have the luxury from hardware, so we must do it ourselves in compiler. So therefore, a traditional loop style, just to note, it comes with a powerful cube unit. That's a big fat matrix multiplier, as well as a vector unit. So to ensure performance, we need some optimizations that can perform tiling, as well as DMA insertion, working concertedly with a traditional loop vectorizer, because it does have a traditional SIMD unit on the chip. So with all that, that takes us to Syclops Converter. So many questions may arise. Why do we choose MLIR? And why do we choose to do a converter from LLVM into MLIR? I mean, there are various historical reasons. One key reason was in the beginning, we were trying to make use of AKG, which was a derivative of TVM to support programming for DaVinci. AKG, having based on halide IR or TVM IR, is at an IR level that's similar to the affine IR. So that sort of set us up to wanting to raise the IR of LLVM to an halide IR level in the beginning. Well, then you say, why don't you convert directly from Clang AST? Well, that's a valid question. And if you had looked at, and we make good use of the DPC++ open source repo, with all the language abstraction, the C++ abstractions that are there, severe operator overloading. So that means if you see a very simple device code with just square bracket, it's not just square bracket, it's overloaded. So you really need to, it's not as easy as converting directly from the Clang AST. You really want LLVM to take a crack at it, to inline it, clean up the IR, and present itself as really an array access to the converter. So at that point, we trade off various approaches, and we decided an LLVM converter is what to a higher level is what we have to go with. We couldn't leverage other work to on the LLVM IR that's given to us from the Clang compiling the complicated C++ abstraction. Okay, so now we have established that we want the LLVM to MLIR converter. Then you may ask, what's so attractive about MLIR that we want to be there? Okay, so that's another question. At that time, when we looked at it in LLVM, there was no tiling path. But that was a year, almost 2 years ago. There wasn't a strong and robust tiling path. But at that point, we know that the affine loop tile is being developed in MLIR. And not only that, the data copy generate to insert the DMA was also a path that's in MLIR. Also, with super vectorizer there, we felt that the three combination really motivated us to go to MLIR rather than stay within LLVM. So with that decision, we arrived at a Syclops converter to raise the IR abstraction from LLVM to MLIR. So there is a diagram to illustrate a little bit about this Syclops program because a host code and the device code co-locate in the same file. So you have a host compiler as well as a device compiler that compiles the device kernel into the LLVM IR, and then we passes that through our Syclops converter, which effectively raises the abstraction to the MLIR affine dialect, and then we are able to enjoy the many MLIR optimizations there are. And there are some aspects of the converter that I want to highlight today, mainly its ability to recover the program after it has been in the very low level LLVM IR. So I will speak on that from the fact the block and control flow reconstruction, the shape of the Syclops buffer, how do you know what shape that is, and the iteration space. Should we want to apply parallelization, we need to know the iteration space. So these three aspects I'll talk about. Okay, let me move quickly. Okay, so as I motivated why we were doing a converter was because of trying to make use of AKG, which is based on TVM, the halide IR, TVM IR. So that's where we started. But that drives the design of the converter to have a base module which interprets the Syclops constructs and the control flow being passed in. And cleanly, we develop different backends for it. One backend is the MLIR submodule that will generate the MLIR affine IR text, as well as the hybrid script submit module that will interact with AKG or TVM. For today, I'm focusing heavily on MLIR, and I will not be covering the AKG aspect. Okay, so there are a few steps in our conversion process. The first step is the pre-processing step. We want to, this pre-processing step is to make sure the incoming IR is good for conversion. So it's a little bit like preconditioning the IR to make it friendly for our converter. It performs two things, conversion simplification passes and control flow simplification passes. So for control flow simplification passes, we run things like loop simplify, LCSSA, that sort of passes. And we also try to simplify some of the select logic to convert Boolean select into AND ORs. So this is just to precondition the IR so that it's more amenable for conversion process. And this is the only place we modify the IR because we want converter to not modify the IR. Okay, so block generation. So what this does is where conversion begins. So we will go over the LLVM IR basic blocks and instruction by instruction, converting the non-control flow instructions to MLIR operations. And we create these MLIR blocks. So one LLVM basic block will correspond to one MLIR blocks. And of course, the instruction and the operation will be contained correspondingly. That's all making great sense. However, the control flow representation of LLVM is quite different from MLIR. LLVM does not have dedicated operations for loops or if statements. So on that front, loop latch blocks or if header blocks are collected and used to generate the for and if operations after all the non-control control flow operations have been generated, and they are placed in the control flow operation block. So at this point, all the operations have been generated, but they are not put in a coherent manner. They are just there, but they are waiting to be hooked into a coherent manner that corresponds to the original CFG. Okay, so that's the generation part, and now we move on to, right. Okay, so now we are going to connect the MLIR blocks and the control flow operation together according to the original control flow graph. So control flow graph is built with the loop analysis dominator tree analysis paths that will let us to build the CFG, and we'll recursively traverse the original CFGs and merging the blocks and inserting the for operation and the if operations where needed. And we keep doing this until all the operations essentially exist within one single function body block. So at this point in time, the block and CFG reconstruction has completed. But one part I haven't talked a lot is about the shape of the pointers and the iteration space. So I don't know if you guys have looked at a SYCL program. So I must show a SYCL program while we are at it. This is, as you can see, that the memory model of SYCL has SYCL buffers. Well, it also has USM, but for this example, we use SYCL buffers. And this is on the left is a 2D SYCL buffers. It's all nice and good. However, you notice that the shape of the buffer, which is the range 32, 32, that information is static, compile time known, but it's known on the host code side. So by the time you get to that kernel at line 15, the kernel code, so that at that time, the range of the SYCL buffer are passed into the kernel function as arguments. So if you were to optimize the kernel function apart from the host function, you have effectively lost the static shape information of your buffer. And as you know, static shape and dynamic shape makes a big difference in the code quality you can generate. So we like to preserve that as much as possible, convey that shape information from the host into the device kernel. Right.
So this ND buffer is your abstraction, or?
All right, it's our abstraction. But let's.
That means that if you have a customer, that you will have to modify the source code before it can use the compiler.
That's right. They would have to use our ND buffer for this case.
Which is
for this case.
portable, right? Cross implementation.
Right. So you can stay with your SYCL buffer and then suffer the dynamic shape, right? Or find some.
Start from the AST.
From where?
The AST and don't lower all the way to LLVM MIR before, so that you don't lose that information. I mean, the question is, if you started from the abstract syntax tree instead of LLVM MIR, would the information that you're losing now, which you're forced to change the source code,
Well, the thing is,
would it be easy to preserve?
well, the thing is, the kernel outlining happens pretty early in Clang. You see that it's a lambda function. It gets outlined pretty early. And the outline function will present itself as follows. So you do get the buffer as a pointer in the range.
The AST before outlining it.
Yeah, you would have to do it somehow. Well, then also you need to look through the levels of abstraction, right? So as I was saying earlier, you see that square bracket of assessor? That's really not an array. That's an operator overloaded of the class called the SYCL assessor. So if you were to look at the AST of that, it's highly difficult for you to, well, first of all, you've got to jump through a few functions to get to the fact. Yeah, so that part is difficult. Yeah. But we would love any ways of conveying the shape information into the device kernel. Otherwise, we just treat them as a dynamic shape buffer. All these buffers are in MLIR memref. There would be question mark. And you know, question marks don't play well with affine optimizations. Affine do deal with dynamic memrefs here and there, but the general support is not really robust as static, yeah. So that was that thing. And okay, so I jumped ahead. So I was talking about the shape of the pointers. So the converter itself has a shape class that are meant to keep the rank, the dimensions, the element type, the address space of the pointer. Yeah, and they are used in the conversion process to generate the memref for that. Let me see, what did I miss? Right, oh, right, and that leads me to the custom abstraction, which I jumped further because I was motivating the fact that every assessor comes in as these kind of argument and the range as an argument into the device function. So that's that. Right, and also because it's 3-dimensional, so while we were creating the abstraction, we made it ND buffer. And there's really not much trick to it. It's really a SYCL buffer containing an STD array, which is really just a C struct containing an array. And as you know, you can do this periodically in the template style. So we did that. And when it comes, the IR comes to LVM, the ND buffer presents itself as array, STD array of an STD array, and all the shape information is part of the type because LLVM is typed. So you can get the type information, the shape from the type. That's much better than having a pointer point to a tons of floats and you don't even know if it's the dimensionality of it. So this is the implementation of ND buffer. Oh, another thing is static parallel for. We do acknowledge this is another thing. That's not very standard conforming. But yeah, that's another attempt that we were trying to convey the iteration space information to the compiler. Otherwise, the iteration space is passing as an argument. So if you want to parallelize it any differently, you would want to know the iteration space. Okay, so having said all that, and some of the hoops we need to jump, just to recap. So we take a Syclops device kernel written on the left, goes through the front-end compiler, and it generates a LLVM device kernel function, and we pre-process it, precondition the IR, and perform IR analysis to get the control flow as well as the basic blocks, and we generate the blocks operations separately from the control flow ops. And at the last stage, we did the CFG reconstruction to link them up together. So that's pretty much the converter. And the converter functionality is pretty much demonstrated using this very extensive case of k-means. That's a Syclops device code that shows conditional branching, iteration, escaping scalars, imperfect loop nest, and the ability of that to convert into the affine dialect. Okay, so zooming through. And am I in good timing? Okay, timing. But yes, I will have another 10 minutes. Now is the exciting part. Now we finally made our way into MLIR. So let's talk about MLIR optimizations. Just a little bit, very quick summary is that MLIR is a multi-level intermediate representation, and it has multiple levels of abstractions. They present themselves in terms of dialects. For our intended purposes, we care about affine dialect, SCF dialect. For those that we cannot, they are non-affine, we have to put them into SCF dialect, as well as the arithmetic dialect for all the operations. MLIR types of interest, we are very interested in memrefs because they are MLIR's array representation, multi-dimensional memrefs, and we are particularly interested if they are static shaped. Although dynamic shapes, we can accept that as well. And the index type is of a particular interest because they are the loop induction variable and used to index into the memrefs. And they are device-specific integer width to the architecture supported with. Okay, well, here is the first time for the picture to showcase the optimization pipeline that we as a team built to support the DaVinci architecture. I guess if you quickly gloss over it, it's really condensed. A few things to highlight is we have created a matrix dialect. It doesn't call it a matrix, but since the term is not disclosable, so I call it a matrix dialect. We invented that to target our cube unit. And we have the DaVinci dialect to handle the DaVinci-related vectorization and all the rest of it. And we make good use of loop tiling, affine loop tiling, affine data copy generate, as well as super vectorize. And following that, you need a lot of lowering passes to convert from your dialect to the LLVM dialect. And finally, the LLVM dialect gets translated out to LLVM IR and flows through our backend to generate the object file. Impressive. So we created dialects left and right. That's what we do. We love dialects. Okay. Right, so I want to talk a little bit about the affine optimizations because it's for those purposes we got ourselves into MLIR. And as I motivated earlier, there is this explicit memory hierarchy management that needed to be done by software. And that motivated why we are looking at memory tiling plus DMA insertion, which brings to good attention of affine loop tile and affine data copy generate. That's just the MLIR documentation on affine loop tile. Okay, before you can make use of anything, you need to know what are the limitations of the existing passes. So we did our due diligence. We studied the affine loop tile and data copy generate. First point, the loop tile only works on perfect loop nests, meaning upon encountering the first non-perfect loop nest, you will stop tiling. Right, and you may ask why? We don't know, because the dependency analysis really does support dependency with the whole dependency polyhedron infrastructure supports memrefs that are not inside perfect loop nests, an analysis of that. So why does affine loop tile doesn't support non-perfect loop nest? I don't know, that's what it is. But it does do very well of supporting dynamic memref shapes, runtime trip count loops, happily inserting min or affine maps for you, not a problem. Okay, so we know about, and one also must know what's the default tiling algorithm as written by Wude. I think he contributed to the affine tile algorithm. So it takes the nth rule algorithm to do the tiling. What does it mean? It first computes the excess factor, meaning what's the memory footprint excess to the cache, how much more in excess you are to the local fast cache. So the memory footprint divided by the cache size bytes. Are you 3 times more or are you 4 times more than the cache can contain? That is your excess factor. And it takes the nth root of that. So the result of it is a square or cubic type of tiling that you have. Yeah, why is that the default? I don't know. But that's what the algorithm is. It doesn't really work for us. So that led us down a path in extending that because the dimension which we want to tile is critically important. That ties in with the DMA. If you tile a loop with some funny number, well, and your DMA has a constraint, you must DMA at a certain number of chunk size, then you are in trouble. So this nth root algorithm doesn't really work for us, and that's also a primary reason that led us to optimize the affine tiling. Okay, let's go to DCG, data copy generate. That's a source of headache of its own. It calls this function get memory footprint bytes to estimate how much memory does a memref take up in this loop that it's chugging along. So for example, if it's chugging along a loop of 32 iteration and you are 4 bytes, so roughly it's gonna take 32 times your float. So 32 times 4, that's rather the amount of memory footprint. But situation gets very complicated. Things are not as easy like what I just said. So, but this is critically important because you gotta know how much data you need to bring in because that's how much DMA you're gonna do, the DMA length. So we analyzed to depth of the limitation of DCG. We found that it handles static loop trip count quite nicely, static memrefs quite nicely in combination with runtime trip count. Yes, you need to know the cases, but when you hit the case of dynamic memref, for example, SQL buffer gives us dynamic memref and runtime trip counts, well, that is of limited support. I mean, it does support some cases to do the data copy generate to put a DMA, but it also hits problem. I do have an example. If time allow, I'll show you guys all these points in the affine code. Well, anyway, I want to motivate our enhancement to affine tile. As I said, if you just tile nth root and pick a tile size oblivious to your DMA ability, then you can generate tiles that you cannot DMA. Okay, so what does that mean? How about we tile the innermost loop? That's where actions are, right? The innermost loop. But if you tile the innermost loop, you may also make a mistake because the innermost loop may not correspond to the innermost contiguous of the memref. For example, the memref innermost dimension is on arc4, but arc4 is not the innermost loop. So the strategy, how you are going to tile, largely dictated by the memrefs, and the loops you want to tile really, they may not be the innermost, but you need to decide, is this loop going to suffer the DMA constraints, or is this loop, you can tile it whatever way you like. So to that extent, we go into backup slides because I had a feeling that time would be running out. So, so anyway, I don't know, that's 30 minutes, so I did not really go into the how, but maybe a quick preview since people seems rather interested and I have time. So we dug into the polyhedral constraint mechanism that's underlying the affine dialect. And we make good use of the Fourier-Munsken projection mechanism to let you project constraints, thereby telling you what are the, what's the word, what are the aggregated, the range of the DMA that you can do. So the work led us to use certain facilities that are already available in affine dialect. We did not invent any of this, but as you can see, we are trying to select tile size S0, S1, putting the constraint that they are bounded by A192, and then we perform projection to figure it out backwards on what are the shapes, to check for legality and whatnot. So that's our current work, just to help us to tile this so that DMA will be happy with us. So I think that's it.
If you have like different memory access patterns, so you have a load where the R4 is the innermost and one where it's not the innermost. So what's your strategy to handle those kind of cases?
Oh, 1 second, let me just go back to that. A load.
In this case, you have to affine load where R4 is the innermost dimension.
So both loops that affected the two loads, innermost dimension will be constrained.
Right,
they will be subject to.
If you have the second load is done the other way, arc3 is the innermost dimension.
Then arc3 loop will be a constrained loop, meaning it will be tiled pretty much the same as all the other loops, except it has an extra constraint that it must satisfy, which is the polyhedral constraint that we showed. So all the loops are pretty much equal. They are equal citizen, except the loops that affect inner dimensions of a memref. They will be subjected to a special constraint. And yeah.
And then you can tile more than one loop.
You tile more than one loops. Yeah, yeah, for sure. So that's our ongoing work, and I believe we are expecting a paper out of it. Yes. Okay.
Just from my own understanding, the constraint that you're talking about is that DMA memory transfer constraint.
The way we formulated the constraint is as follows. So the constraint we formulated is the S0 constraint, but we use the projection to get back to get the range. And what we needed to find is the lowest and the highest, because DCG operates by union or compounding all the loads. So should there be overlap, they don't bring it in twice. So you will compound from the lowest bound to the upper bound. So we need the compounded lower bound to the upper bound to be divisible by the DMA's size, because DMA may want a certain chunk. So you want the lowest to the highest to satisfy that constraint. Yeah. Right. Let me see. Just see if I skip any good stuff that I didn't talk about.
It's all good stuff.
It's all good stuff. Right. I think pretty much that's it. Yeah. So if any questions? If not, thank you for listening.